Today I'm going to talk about efficient hardware design using hardware description language and high-level synthesis to bridge software expertise to hardware acceleration. Many of the related works are done during my undergraduate study at Southeast University. Yeah, let's start. So here is the outline that I will first talk about why we are talking about hardware and why even software engineers will sometimes need to have some knowledge of hardware, and also how to design hardware architecture that is really efficient to implement. And there are also tools like hardware description languages and high-level synthesis, which is especially useful for software engineers to implement high-level algorithms into hardware to achieve high efficiency. And I will also talk about a little about design automation, because nowadays large language models it's very hard, and we will need to consider that at least, if we want to write code. So we certainly want that. And so first is that we want to know that there's a shifting landscape of computation, and I think everyone is quite familiar with this. So from the hardware side, that Moore's law is slowly, because the transistor density is already reaching some kind of limit that current technology is already arriving at this step. And there is also the power density problem, because power is sometimes overwhelming and can be a bottleneck. So the performance gains from general purpose CPUs or GPUs, they are actually diminishing. And in the meanwhile, there's a rise of data intensive workloads such as AI, ML, big data, IoT. So there are some kind of work that will require very large data computation, and every big company, they are committing to buy GPU. So the computation is quite a big thing. And there are also cases that we need specialization, and CPUs and GPUs, they are not always optimal, because we all know that the speed may not be very promising. And domain-specific architectures offer paths to continued performance and efficiency gains. If everything is working like a chip, it's going to be very efficient, both in power efficiency and in time efficiency. So it's very promising. And there are also attempts in industry. So for example, Google has introduced the TPU, which is essentially an IC chip that can do computation acceleration. And there are also other tools from these big companies that will likely to transform your algorithm design into something that can run on accelerator targets. So
what is the HLS for ML in Google? I've never
oh
heard that before.
For HLS for ML, there is an HLS2 high-level synthesis tool that will transform the machine learning like a deep neural network into a one that can run on their specified
So
targets like FPGAs.
basic on the Python code which writing for ML system.
Yes. So they want to transform that. They're not only able to run on GPUs, they can nowadays run on FPGAs for acceleration with ease.
That's very powerful tools.
Yes, but there may be a lot of problems when we actually use that. Yeah, so we have to be
So why don't
careful
you
here.
recommend me in my previous project that I can transfer the ML codes to LHS?
Yeah, I think for Vitus, this tool, this is more, they can work better with their own FPGAs. So I'm not very sure whether the HLS for ML will.
How is for no not for general FPGA designing, just for Google TPUs or their specific devices?
Um, well, they claim that it is general for many FPGA targets, but their performance with um, AMD FPGAs are not guaranteed, because Vitus is specifically designed for AMD devices.
Okay, so in nowadays we generally using the FPGA designs with AMD Vitis and
Yeah.
Shadow, right?
Yes, that's true. Because HLS4ML is some kind of it's somehow similar to academic designs here. So it's not very, it has not been very proven to be used for in real products. But
Okay,
we can see whether it will work.
okay, see.
Yeah, so there are also actually other platforms that are not only considering FPGAs, they can also run other accelerators as a framework. So they may be interesting for um, the research here. And now let's ask a question. What if you could design your own chip? So now we have the algorithm in hand because we all devise a lot of efficient algorithms. And for software developers, they write software for fixed hardware normally, because if we are setting the target a CPU or GPU, it will just run as what we believe that it will run. And for hardware designers, they sometimes design the hardware itself, because for a chip, we have um, to put the transistors, then it's their design task. And if there are such kind of full stack engineers that can do both in an orchestrated way, it will be amazing. So let's consider here are four targets that quite represent everything that we use for computation. So from CPU and GPU, they are quite flexible because almost every code can run there, and it's quite known that they will work. And if we use IC chip like ASIC, so application-specific integrated circuits, so that's like that in our mobile phones for so they will be very efficient, but it's not very flexible. We can't really hack into that, and we can't run our custom code in that. So, and there is also what is very attractive is field programmable gate arrays FPGA, which can be reprogrammed and run with very high efficiency. But yeah, so it can be reprogrammed and it can be efficient. So it is something that stands at a compromise between flexibility and efficiency. So, and for research projects that evolve very quickly, FPGA is definitely a good choice. So let's talk about FPGA first. So imagine that we have a vast array of configurable logic blocks and programmable interconnects, then we can somehow create a complex logic that will run an algorithm ultimately. So that is very attractive. And and unlike application-specific integrated circuits, which are fixed and it's a chip that is already there, and we can do nothing to change that, FPGAs can be reprogrammed for different functionalities. So we have um, algorithm 1 and algorithm 2, and we just need to program the FPGA, and then it will run as our design. So that's good. And key advantages for custom architectures is what FPGA can very good at to achieve, because it tailored to algorithms. So we design the hardware in FPGA directly for specific algorithms. And FPGA is also great at achieving massive parallelism. It can exploit fine-grained parallelism inherent in algorithms. And there is a lot of optimization in their synthesizer to perform the transformation from your design to the hardware that's going to run on the FPGA. And it's also very good at achieving very low latency. And data can flow through custom data passes without OS overhead or general purpose instruction processing. And so the clock rate can be very high for FPGAs. So that will make the computation very low latency and also high throughput as well. And it also has power efficiency. And because the logic, the hardware, it is optimized for specific operations, so the overhead is significantly reduced. So FPGAs offer a blank canvas for digital architects. So whenever we think about we want to write an algorithm, we also want to do is like we are like a digital architect. We want it to work on a real hardware that can render the algorithm to real life. And here is an illustration of FPGAs. So this is a very simplified one. So let's see that here we have programmable interconnect. So in this gray square, that the wire, they can be connected in a programmable way. And we also have logic blocks. So there are a multiplexer, lookup table, flip-flops, and everything. And they can compose the logic that will be in the algorithm. And
A
there are
question here.
also, oh,
A question here is that I think the chips on when manufacturing in initial stage, there will be have a fixed interconnect with some fiber or something to connect them together. So how they become programmable in interconnected in in future programmings in FPGA devices or Verilog or some HLS. So how this kind of chips to be programmable? My question.
oh, so these chips to be programmable, there are a lot of hardware IC things. So they play with the transistors. When they program that, they use some kind of to change the state of these interconnections between the wires. And for we as the end users or just a high level digital design, we do not need to dive so deep into this kind of details as they are currently very well handled by the tools that we are using. So if we are targeting AMD FPGAs, that the Vivado tool, they will handle how to do this very well. So we
So
only
I
need
think it's
to,
more complicatable than using if before compare with you designed specific chips like GPUs or CPU, right?
yeah, it's kind of more general and yeah.
Would be more
And
complex or more simple.
well, it will be more complex because there have to be some redundancies than the custom design IC chips.
Okay.
We have to use these standard of logic blocks and interconnect them together.
Okay.
So there
Yes.
is, yeah. So sometimes we just only utilize some part of the FPGA to achieve some certain algorithms.
Okay. I see.
Yeah. And here I put a list of more things on FPGA. So configure logic blocks in the connect IO blocks. There are also DSP blocks that they specialize for high performance arithmetic operations. So the multiplication, they can be done with DSP blocks with very low latency. So this kind of thing, they are especially in the FPGA. So because this kind of operations a lot, so we do not need to use IoT or flip-flops to create such kind of logic, and we can directly use this. And there are also memory blocks and clock management. There are also there are also memory configurable, I think, or configuration memory. Yeah, it's to store the configuration data for the FPGA. And there's also power management. And for powerful FPGA, there are also embedded processors in that. So they can have an ARM core near the FPGA, and they can some kind of communicate. So that's awesome for field programmable gate arrays. And now maybe we can still think about having some kind of ASIC because like Apple, they have some claim to have some neural chip. Yeah, but they're most suitable for high volume production with a fixed design. So for Apple, that they can ship that with so many mobile phones. And for most cases that there is no such kind of high volume for a fixed task. And for like baseband signal processing or video codecs. So such kind of fixed functions, accelerators, the ASICs are very suitable, but mostly if we are targeting fast evolution of AI ML algorithms, ASICs will just get outdated so quickly. So we need the reprogrammable capability with FPGAs, and it's more flexible and cost effective. And nowadays, FPGAs are more capable because the advance of technology. And there are also very interesting combinations that we can have both FPGA and fixed ASIC cores like video codec, they work together. So that will be good for actual system integration. And now that we know that we can use FPGA to achieve hardware accelerations, we want to know at least some tools for digital design. So for software, we just write high-level language. So we write C++, we write Python, and we do not write the assembly code. And similarly, for hardware, we do not just directly put the transistor there or know how the interconnects are configured. We just describe the gate logic or even higher level behavior of the hardware. So it's some kind of a like an algorithm, right? So it's not so difficult. And for hardware description language and high-level synthesis, there are tools. So that's what we use. But for the hardware architectures, we still need to design that. Even if we have a very powerful compiler, we do not have a very good code. Yeah, that's the same thing. So let's dive into the hardware architecture. So the hardware architecture is key to efficiency. We always need to remember that. And so even we have a very great algorithm, if not implemented properly, it will not be running in hardware with high efficiency. And another thing is that even if some algorithm is proven to be efficient on software side, CPUs or GPUs, that is general purpose processors, they are not necessarily good for FPGAs because the inherent difference between the general purpose processors and the FPGA logics, because we have to design with the hardware architecture here. But if we know that these certain things very well, we can achieve it better at least. So first thing that we need to achieve high parallelism, because FPGA is very capable at high intensity processing tasks. So it can process multiple operations simultaneously. We have data parallelism, and we can also achieve task parallelism very easily. And also the very important thing to increase throughput is pipelining. FPGA has very high clock rates, so we can have overlap execution stages for high throughput. We can have operation pipelining, so we're breaking complex operations into stages. So if we want to do the multiplication, we may not do it in one clock. We may break that into 3 clocks, and it will just get pipeline. So it will run more efficiently. And there is also the thing that we can strategic register insertion for improved timing and throughput. So this is even if we have an algorithm, how we can extract each step of the algorithm and make sure that each step is not taking too long because we want a fixed clock rate. And the third point is memory hierarchy. We want to optimize the data access patterns for registers, caches, local buffers, and external memory. There are a lot of them, and the speed to access each one of them is different. So we have to design the algorithm carefully. We try to minimize the expensive memory access and try to keep everything in place. That's the best. And the fourth point is that we want to have data flow optimization. We want to minimize data movement. So that's correlated to the third point. and we want the processing units near the data sources. This is also true for how FPGA synthesizers interpret our design. And for data flow optimization, the direct streaming between components is also very useful because so for one use case is that we want to have to balance the rate between each step. So if there is one bottleneck, then everything is just constrained by that. So that's not good. The fifth point is that we want to have some kind of a resource sharing. There is a trade-off between the area and performance. And if we have some kind of reconfigurable model, then it will be useful to achieve efficiency. And the sixth point is specialization. We certainly want to have custom data policies for specific algorithms. So it will look a lot different in the hardware side.
Okay,
So
so
that, yeah.
Yeah, you mentioned that the hardware architecture design is key to efficiency, right? So
Yeah.
then which phases we need to design the hardware architectures? I think that we just writing some C++ codes or Python codes to implement it at our algorithms or logics to doing something like machine learnings or model servings or something. But when we don't do we need to focus on the hardware architectures in the software designing phases?
Yeah, I think that's a quite good question. Because for first, before we are designing the hardware architecture, how these are optimized, we first need to have the algorithm. An efficient algorithm is the basis for everything. And nowadays, there are a lot of useful tools that can transform some fixed pattern designs into hardware in an efficient manner. So for deep neural networks or some models, there are tools that can transform them from the software code to the hardware architecture. So that's the very
So
good thing.
so it's basically based on the compiler to how to compile our codes or something like we writing very roughly in software.
Yeah, but similarly, we all know that even if the compiler is very powerful like C++, we can also write very bad code that executes with very low efficiency.
Yeah.
So it's the same for the hardware architecture. But if our use case is very simple, like it's only a neural network that one single neural network that's working, then it can be handled well by the compiler. But if there are
Do you think
multiple,
So do you think it's possible that we can translate the bad code into more excellent codes with some large language models? Like I transfer the C++ code to more hardware architectures efficiency like structures, so bit more easier to compile into this kind of efficiency hardware architecture.
yeah, that's a
Is it
very
possible?
good thing. Yeah, I think it's possible, but not so easy because we don't really have as much resources for training here because many of them they are closed source and the open source code base is very small here. So we certainly need some other ways, including expert knowledge to do such kind of optimization. The current tools, they are already trying to extract the internal logic of your hardware design to get an optimized result, but they can be very efficient if the architecture is not designed properly. So the top level architecture is the most important. It's like how we transform the algorithm into large blocks, and the arrangement of the blocks, they are typically not handled well by the compilers because they really never know if the pattern, the modules, how they interact changes, because the results will change accordingly. Whether that's the correct answer, the compilers do not know. So, so if we are like considering deploying several neural networks and they are working interactively with each other, then we have to handle the top level architecture well and considering all these kind of things. And when writing the code, we want to have a basic idea of how hardware works, and then our algorithm may not be so hard for the compilers to optimize. Because sometimes if the code that we write, that's the instructions for the compilers, they just can't follow that. They say that it is impossible to achieve that, so I give up. Then the hardware even fails to generate that. That's bad. So we have to get the hardware right, architecture right.
Okay, see. Okay.
Yeah. So, but with nowadays it's easier. So like 20 years ago, the experience is worse. Many things that compilers will just complain to you. No, 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 you can't do this. And nowadays they are somehow more clever.
There's some locks, right?
Yeah. So here I give an example of how hardware architecture impacts and how it is somehow different from the algorithm implementation. So we'll consider a very, very, very basic case. That's the general metric multiplication. So we are very familiar with metric multiplication. And for software implementation, we know there are many, many algorithms that will reduce the complexity of metric multiplication. But for hardware, we are not exactly doing that. Because of the hardware, because of the characteristics of hardware, we have the parallelism instead of the fixed number of threads or cores that provide in general purpose CPUs and GPUs. So we can have higher parallelism, but we do not want the data to be moved so frequently. So for metric multiplication in hardware design, there's a very well-known structure that we can use a systolic array to achieve that. So we have an array of processing elements, so they work simultaneously. And the result just directly comes from the processing element. And the input data gets streamed in. So this is metric A and this is metric B, and they all get streamed into the systolic array. And in each clock, the data is passed from left to right, from top to bottom. So in this direction, there's not a lot of data movement. So it's very elegant way to get the data in and out, and it will perform the multiplication of two scalars and add them to the sum. So after this gets streamed all over till the end, the result is obtained. So this is very efficient in hardware design. And this is very scalable as we can expand the array size to handle larger matrices. And what makes things better is that for matrices with special characteristics, so if the input matrix is symmetrical, we can further optimize the systolic array to reduce its size. So, but yeah, so this in this example, I want to show that for a given software algorithm, for the hardware design is somehow different, and it will really impact the efficiency. The good news is that when we want to design hardware, we do not need to write such kind of so small details. We just let the compilers do the jobs because they already do this inside their library. But yeah, so this is just an example. But for higher level things, we may also keep those concepts in mind and try to design such kind of efficient architectures. And yeah, and so after example, I want to show that there is one thing that is almost unavoidable in hardware design for each kind of module. So we certainly need to consider the finite state machine that whether it's or whether it's so obvious to have such kind of, or it's just hidden beneath the code. So there are many inherent usage of the FSM. So for FSM here, I show an example with a coin controlled turnstile. So there are two states. There are locked states and unlocked states. And we may use the coin and we may push the button. So if the machine, the turnstile is locked, we insert a coin, then it will be unlocked. And if we put another coin into that, it will still be unlocked. And if we at the unlocked state, we just push the machine, then it will move and then it will get locked. So for the hardware design, we want to, we actually know that there are a lot of states, and there are also ways that will get the states transit from one to another. So that's how the hardware is working. So if we use a 2 or 3 process finite state machine, and we can have this kind of two things. The first is the sequential logic. For the hardware, that the sequential logic will store the current state, whether we are doing task A or whether we are doing task B, or in other words, whether we are now at the idle state or we are busy state or we have whatever state. So that's the sequential logic. And there are also the case for combinational logic. So this will determine the next state. So with different input, we will have different state output. And we also have a output. So if the result, what the result will be. So for a logic like we want to add number A and number B, so that's combinational logic because the result of A plus B will just be simple as the combination of these two values. So that's finite state machines. And if we are going to creating something very elegant with the time series, we certainly want to have some kind of FSM design. Oh yeah, now we have already get the knowledge of how the hardware architecture would be. Let's dive into some kind of tools that we may actually use to create that kind of efficient hardware. So we first have the hardware description language, HDL. So for HDL, it's just a specialized program language used to describe the structure and behavior of digital circuits. So we can write Verilog, VHDL system Verilog. Yeah, there are a lot of them. And different from software languages that we describe the parallel hardware structures, not sequential steps. For writing C++, normally the code will just execute from top to bottom, from line 1 to line 100, and that's how it works. And we can have breakpoints to check what's going on. But for hardware, it's not. They're not waiting for you. This logic is doing its job, and another logic is doing a different job, and they do not know each other's existence, and they will just compete with each other. So yeah, they're doing parallel jobs. And the second thing that the hardware description language actually represents the physical circuit components and their connections. So yeah, so we need to keep in mind that they're describing how the hardware works. And another thing that timing explicit and critical. Each job within one clock must be done in that clock. If it can't be done, then the logic will be wrong. For software, we do not need to worry so much about this because for general purpose processors, they will handle that well in their architectures. So very expensive logics have to be dealt with carefully in hardware description languages. We want to break a complex calculation into several steps, so each step it will be achievable within a certain time. And there is also the difference in the abstraction levels in HDLs. So we may have some behavioral representation. So we can just write algorithmic description. So for two numbers, we can just write the star symbol and they will just get multiplied. So that's the simple way. And we can also say the register transfer level. So that's the RTL. And we want to see how data flow is going on between the registers. So that's more explicit than the behavioral model. For behavioral model, we rely on the compiler to transform that into the RTL. And for some special cases, but we may not need to test that so often, so that we can also use the gate level representation. So we can just use the XOR gate or NOR gate, and yeah, we can do that. So that's powerful of HDL. You can use different kinds of abstraction levels all together in the code. So that's interesting, right? Yeah, and for HDL code, that there are two important logics here. As I mentioned before, as a finite state machine, the HDL is especially useful to represent such kind of FSMs. So we have combinational logic that is direct memoryless Boolean functions. So the output depends solely on the current input value. So that's simple. Yeah, if we have A and we have B and A plus B is always that value, can't be other values. So yeah, only depends on the current input values. And there is also no memory or stage for combination logic. If the input changes, we don't have any way to store the thing. So in the hardware level, if the voltage changes, we can't really store that in the combinational logic. And if we want to have Verilog code, so for here, we just use the output signal will be the AND operation between signal A and signal B. Yeah, that's simple. We can read English. And second point that is we also have to have sequential logic. We need to hold the state triggered by clock signals. So at specific clock transitions, like if we have clock at rising or falling edges, we want to update the state value. So it can keep in the register for one clock. So that's important because not every logic can be represented using combinational logic. We have to do it step by step, then we have to use the sequential logic in that cases. So the values stored they just between the clock cycles in the registers or flip-flops. Yes. And the behavior is defined in always at pulse at clock. Oh, that's easy to understand. Whenever there's a positive edge of the clock, we will do something. Wow, that's easy to understand. Yeah, but writing code will be painful, but understanding that there's oh, interesting.
Okay, I have a question. Is that when we have algorithms writing in C++, and then when we need to writing some codes like Verilogs, because you have HLS, so we can translate our synthesis to more hardware codes. Then when should we focus on the hardware codes like Verilogs or to care about the clocks blocks?
Oh, yeah, that's a good question. So we're using hardware description language here, writing Verilog codes. We're actually inclined to deal with the very details of the clocks. We want it to be very precise in timings. We do not want it, if we want the design to be done in 100 clocks, we do not want it to be done in 101 clocks. So there are use cases for high-speed interfaces. We have to have very precise control of this kind of logic. So at that time, we certainly need to write some HDL codes. So they are useful for interfaces. And for the algorithm logic cores, we may sometimes using high-level synthesis that I will mention later to perform the tasks that will be easier to implement. But in the old days, there are no high-level synthesis, so they have to design every algorithm details in this kind of combinations. Yeah, let's continue. So there are also some other concepts that are relatively easier to understand. So we have modules. So for a hardware, we can encapsulate units with defined interfaces of input or output. So yeah, that's easy to understand. So like we are having a function and it has the arguments there. So that's easy. And for writing HDL is one thing that we need to be careful with, that there are blocking assignment and non-blocking assignment. So mostly for sequential logic design, this is very crucial for sequential logic, is that we certainly do not want one operation to block another operation. So they need to be run in parallel in most cases. So that is non-blocking assignment. And if we really want it to be sequential, and mostly that's in the test bench, that they can be blocking. So this need to be minded that in the future you may encounter. And another thing, that simulation is different from synthesis. So not everything that simulates can be synthesized into hardware. So we want to write a code, we say that at clock time, the signal need to be high. However, this can't be synthesized into hardware because it does not really control the clock. Wait, what time is it now? They do not know. So simulation and synthesis, they are different. So we need to write code that is synthesizable in module designs. And for FPGA, that we first write the HDL code, and then we do the functional simulation. We verify the logic, it works, before we are deploying that to the FPGAs. And then we can convert the HDL to optimize the gate level netlist that's handled internally by the tool chains. And we will do the implementation that will translate the netlist to target device and do the placement optimization and do the routing. So as we know that there are programmable interconnects. So all these things will be handled internally by the tools. And the fifth point that we want to do the time analysis. We want to know that whether each step is can be performed within the our time constraint. And we want to locate the critical path, that is the bottleneck, constrain the hardware efficiency. And after that, it will be simple. We just generate the base stream and program device. So that's great. Done. We want to see the board running, right? This is not the same thing for application-specific integrated circuits, because everything is fabricated. We have to be more careful in every step of the design. And to make things worse, we have to put the transistors carefully, and not every tools can do that automatically. So let's thank FPGAs. We are saved. We don't need to care so much about the integrated circuits. Yeah, now we have endured such pain in understanding hardware description language, so we can now go to high-level synthesis. What a relief! We can finally write C++. Yeah, it allows software developers to create hardware using familiar programming languages. So we don't want to learn Verilog? Fine, just write C++. So it will just be faster development cycle. So it will be hours versus days that we do not need to consider so much about, oh, what to do at this clock cycle. I don't know. What's wrong with my final state machine? Oh my God, my state just get boomed. Oh, for writing C++, everything is under control. So we have higher level of abstraction. So we can easier debug. So we just use the clone compiler to do that. So that's easier. And we have the software to hardware transform automatically. So if we want to know more about that, there's one sick book, more than 300 pages about this. So parallel programming for FPGAs, and this is open access. So if we are using FPGAs, mostly we're using the AMD devices. So their toolchain Vidas HLS provides such kind of workflow. So we design a C++ with some certain kind of directives, because C++ code can be interpreted in hardware this way or the other way. So we want to add some directives telling them that how this code should be interpreted. I will cover later. And then we want to do the C++ simulation. We run the C++ compiler and we get the result. That's cool. And then we synthesize it to RTL. It will get transformed from algorithm to the hardware. And then we can do the core simulation. Software and hardware, they will co-simulated. Whether our hardware results match the software results. That will be the key. So sometimes if costing fails, that will be bad because we really can't fix that as it is internally controlled by the compiler, but we certainly want to verify that. And there's the fifth point that we want to do the implementation. Yeah, that's simple. After we get everything, why not transform that into the base stream that can run the hardware target? So that's the 5 steps. That's quite easy to understand, right? But now we have to face the sad fact that C++, but they're not exactly C++, because of the conflicting nature of sequential software and parallel hardware. When we write C++, it should be run in sequential logic, not parallel nature of the hardware. And to make things worse, there are more differences we have to think about. First is that there is no dynamic memory allocation. Whenever we want to have a memory, we have to declare that and create that explicitly. And there is also limited recursion support. For recursion, the hardware say, what is recursion? I don't know. I just do my job. So yeah, so this is difficult. And there are also cases that when running C++ loops, they are actually loops that run from top to bottom, but in hardware, sometimes you need to be unrolled into parallel hardware. And sometimes function calls may be inline as circuits, so this is also done in software actually. And another bad thing that this really called poor standard library support. If you want to do this, sorry, we do not support that. That's bad when we want to devise our own algorithm into hardware. And there are also common pitfalls. So if we write the high-level synthesis code in a sequential thinking mode, it can sometimes lead to poor hardware because the data dependency really matters. If the data, if every other step depends on the previous step in your code, the high-level synthesis tool can't really transform the code into the hardware that they will run in parallel. So when we write the code, we want to minimize data dependency. So this is important. So yeah, like writing the algorithm that will run incrementally, that will be very important. And also that the bit width optimization is very important here. Yeah, so in machine learning, this is also important. Yeah. And like GPU runs, we certainly want to avoid loops as well. Yeah, so this is the same. And some logics may not be synthesizable. For example, a pointer to a pointer may not be spotted. So you have to get through all these difficulties. So the bottom line is that it's important to remember these following things using high-level synthesis. Is that high-level synthesis tools translate direct algorithm implementations. So it really don't know too much, just what you write. And hardware-aware coding is required So you need to understand the architecture implications to ensure the performance. So naive implementation will not get a very good results. So if you have that in mind, you can write the code and you need to put some certain directives for the HLS tools to guide the synthesis process without changing the functional behavior. So for example, you need to tell them what the port is. So you want to say that the interface is the axis and the port called data. And you may also want to tell that how the loop is optimized. If you want the loop to be pipelined with an interval of 1 clock, or you want to unroll the loop into factor 4, meaning that there are 4 steps that are running in parallel. And there are also array optimization. So for the array that you may want to partition that. And if it's not partitioned, then it's in a block RAM. For block RAM, there is only 2 I/O ports, so you can't access the data simultaneously. But if you want to partition that, so each one is implemented on its own RAM, then you can access that easily. So this needs to be considered for designing. So sometimes you may not notice what is constraining making your loop can't be pipelined. So this might be the reason because you can't really access the data. And you also want to create some kind of data flow, something in the code here. They may run in parallel in some kind of way. So that's the data flow pragma. And they will cause the results utilization difference and the throughput will also be different. And latency and clock frequency you can achieve due to the critical path. So they all changes. And there is the fundamental trade-offs. More parallelism, it will have higher performance, but more resources. So for FPGAs, if you can have the resources, then you can certainly do the parallel thing. And here is one thing that we need to be careful. My aforementioned the pragmas may change in the future because the tools just evolve so quickly. So definitely, if you want to work on this, we need to check out the user guide for latest information. Yeah, here's the time to sell my own works. So I previously did this one, a small project that creates a library called Flames to do the linear algebra with matrix empowered synthesis. Because as we mentioned before, there are so many things to vary about. There's so many fine tunings. If we have metric optimization, metric calculation, can we do it in a more simple way? We do not want to write functions. Can we write it into classes? Or can we use template-based ways to do this? Wow, that will be interesting to design. So now I created the library called Flames, and this is how it actually works. So I have everything encapsulated in a class named mat, and we can access its element via the C++ operator. And we also have tensors that have slices of matrices. And we also have the view class or the ref class that will not copy the data so often because copying data is expensive. So if we can use the view to abstract such kind of thing, for example, if we want to represent the transpose or just a column of the matrices, we just only need to change the logic of accessing the address of our RAM instead of just directly copying all the RAM data into another one. So that will be easier to do with this. So, but as we know that setting everything in classes may not represent everything. So this work is just a proof of concept thing that showing that the class and the template-based ways for high-level synthesis, it works. And I'm trying to make the algorithm easier to implement. So for example, there is an algorithm called Newman series approximation represented that to do the matrix inversion. So for some certain kind of conditions of the metric, we can do the inversion this way. So yeah, so this is some kind of algorithms, and we can write the formula in these steps. And with the proposed Flames library, we can do things so simple. And we can even use the auto to define the tab. So we can take the diagonal vector of the matrix and get the off diagonal ones, and we do the inversion of the diagonal matrix, which is very simple. And we can do the multiplication and do the recursion that will multiply the matrix and add it and do the multiplication and addition. And finally, we'll have the result. So this is a code writing in Flame. So this is very simple, and we're not even thinking about we are writing in hardware, and they can actually be synthesized into hardware with high efficiency. So that's what I did here. But for product level product things, they may not be useful as so many engineers will tackle these kind of things. But for researchers, for quick prototype on FPGA to demonstrate that our algorithm can actually work on such kind of target, this will be useful.
So you
Um,
just this code in your own designing into the C++ library.
yeah, that's true. So I designed such kind of classes that will internally that will choose the corrected overload functions for the optimized operations.
So I saw you had just published a paper like in like some trends I just noticed. So how do you claim your contributions or innovation in this kind of implementations? I think it's quite
Oh,
engineering works.
yeah, so this is Express Braves paper, so it's only a 5-page short paper. So I'm just showing that this one works as because this is the first work that actually tries to do this kind of things. So I think this attempt might be interesting for future development. So maybe sometimes when the engineers from the AMDs, they find this interesting, they may
Oh,
implement such utilities.
got
So
it.
this is just a proof of concept. For undergraduate students, this is quite interesting to do, and we work with some other students to
Yeah,
get this done.
exactly. So you don't need to mainly do some big progress, just showing our case study, right?
Yeah, just
Okay.
a small case study showing that it works.
It was, yeah.
Yeah, so that's amazing because there are so many difficulties. So yeah, so here's one time trace showing that our NSA can be transformed. So there are some preparations, and we do the first iterations, and there are iteration 2 to 4 running.
Yeah. How do you
And
get this picture? It is
oh,
ILA simulations.
oh no, this is the HLS simulation. So after call simulation, that is the software and hardware call simulation, we can have the timeline trace showing each step of the algorithm, how and how it maps to our original code, that we can say that each step how
So it's just
much.
a simulation not running in the FPGA chips.
Yeah, this is simulation showing that, but
Okay.
it will be the same to run in FPGAs because now after call simulation, everything the timing thing is fixed, is determined by the tool.
So it will be take a long times to doing the simulation task in implementations, future works, like just if you implement it in FPGA, it would be take more long times to doing something like this.
Yes,
Or
yeah,
if we
because
can doing such things in real FPGA chips.
yeah. So for hardware design people, that mostly simulation or implementation will be everything because running on FPGA is mostly some kind of verification because if the Vivado toolset tells you that this one will work, then mostly it will be able to work. Because at that time, we do not even have powerful FPGAs at that time, so we can't really do the verification. So that's very sad thing because my undergraduate advisor spent all the money taping out IC chips. So
Oh, that's a T, right?
so for us, we do not have such kind of equipment, so we can't do that. So we just stop at the implementation. Um, that's not
Okay.
run on real FPGAs.
Okay, so you, in a paper, you just need to show the simulation results, and we can get very good feedbacks in review phases.
Yes, yeah, for circuits and system society, that's mostly enough. But if we're for like a solid state circuits, then they certainly want the tape out result. They even think FPGA result is not good enough.
Okay,
Yeah, so for small papers that
interesting.
we can just do this.
Okay,
Yeah, and when doing the engineering works that we need to have the optimized RAM usage and we can have the parallelism configurable and the metric operations they are optimized because we have function overloading. One special thing that we need to know that there is no return value optimization offered by AMD HLS tools directly. So when using the view and ref classes, so we fix this return value optimization problem. And there are certain limitation of Flame. So this is just a proof of concept. So not all operations are covered here, even though there are already nearly 10,000 lines of code. And the data streaming is also not considered because in our design, we just assume that there's metric and everything is stored in RAM. But in real cases, data sometimes are just streamed in and streamed out in there are certain shapes. So we do not consider this. And if we consider this, it will be much more complex. And the third point is a quite headache because Pragma's configurations are mostly limited to the global scope. The parallelism can hardly be fine-tuned for each fragment of the code. And for our design, there is no way to mitigate this. So
makes
these
sense.
are the quad limitations. And yeah, now I want to talk a little about the design automation because we certainly do not want to implement every details ourselves. Uh, but I have to come to this sad fact of Copilot integration that it's very difficult to get AI tools to write correct and efficient implementation of hardware. ChatGPT, Cloud, and Gemini, they all fail to write some even simple modules. They are trained with very little accessible RTL code, that's bad. And hardware requires precise timing, resource awareness, and physical constraints. So mostly they're case by case implementation optimization. So they can't really capture that very well. And the AI tools, they also struggle with synthesizable and simulation only constructs. So they can't get things right. So currently the best practice is to use AI for initial templates and algorithm sketches. rely on hardware expertise for implementation details and transitions. But whenever we encounter a problem, a bug, we may ask for their help. Maybe they have some insight into that, but we can't rely too much. But now if you are working on AI and large language models, there are potential ways for you to help the hardware designers to get these things working. So large language models research within the hardware communities are mostly constrained in utilizing the black box tools. They just do the prompt engineering to try to make the AI tools write better hardware codes. But there may be more systematic ways to do this. And you may do this. So let's put away the AI tools. There are also embedded domain-specific languages. So for embedded domain-specific languages, there are specialized languages embedded within a host languages. Because writing Verilog, it's very difficult to get it parameterized. When the metric dimension changes, our design has to be changed. So that's very bad. So we can combine the host language power with the hardware abstractions. We can calculate some things in Python, for example, and then pass the value into the Verilog code. That will be interesting, especially we want to scale it up. And so we hope to achieve automated design generation and verification, and as well as tight integration with software into ecosystem. So we can write test benches in Python instead of Verilog. That will save a lot of energy. And sometimes there's also type safety and compile time checks. So this is totally changing the hardware design scene. Now, notably, here are some hardware embedded domain-specific languages. So there's a Chisel. I don't know how it's pronounced, but it's a scalar-based hardware description languages. So it's it's designing scalar, and then logic is designing that. And there is also my toy languages. I just write a very simple interpreter for this to transform the parameters for Verilog targets. And more recently, I devised a Rust library that will do the Python templated Verilog that will try to transform the code design with Python parameters into Verilog code that will get into synthesized into hardwares. So as an undergraduate student enthusiastic of doing every software engineering things, so I do the such kind of tool that will make you configure the parameters and write a CMake style makefile for the project and transform that into the get into the real Verilog code, and spend some time making the command line interface elegant. Oh, what an undergraduate is saying. Nowadays, researchers won't focus on this, but yeah, for undergraduate students, it's interesting. So more recently, I devised such kind of library for my own use. So this is a Python templated Verilog. We will use Rust to generate the Python file, which will run to get the Verilog code. And in the meanwhile, we'll also get the instantiation information, because for the module, it has embedded modules. So the super module will have a smaller module in that, and we'll have an even smaller module within that. So there's a hierarchy there. So the instantiation will be obtained for the other uses. And here is the example syntax that this is a Verilog, and we have a variable substitution in the Python that will run the a equals 1 plus 2, and we can also embed Python blocks within the PyTV code. So that is something useful when we want to scale up the hardware design. So now we will arrive to the conclusion. Before that is the future possibilities. Um, so I can think of something that might be interesting doing in the future. So when we do the system integration, that we have to acknowledge that CPU and GPU, they are very useful. And if we can achieve similar CPU, GPU, FPGA heterogeneous platform, that would be great. And if we also have an automated hardware software co-design framework that will transform our machine learning designs in software into efficient hardware that run in real time, this will also be very useful. And from the architecture side, if we can achieve system-on-chip platforms, bridging software, hardware communities, that will be very good. And there are also cases that we may use diverse applications like smart and IC. Yeah, so FPGAs are good at this sense. Yeah, we may explore how they will get interacted with the network thing. And I think there's a lot to do there. And they're also about hardware-aware software. So even if you are not diving so deep into the hardware design, that can we design an ML framework that will work well with naive hardware acceleration passes? So we are optimizing our code for GPUs, and is it possible that we can optimize those code for FPGA target as well? And yeah, and then also the point from the design automation side, if can we do the domain-specific compilers optimizing for custom hardware and automated hardware-specific code transformations, or can we do cross-layer optimization spanning software hardware boundaries? So there may be many things to do if you want to dig into, or not just verify your algorithm on the hardware so you can claim that it is really working on hardware. That will be good to see. So here are some key takeaways. So with Moore's law slowing, specialized hardware offers a new performance frontier. Yeah, specialized hardware, especially FPGAs. So it provides a flexible middle ground between general purpose processors and ASICs. We certainly do not want to spend 1 year just to tape out one IC chips. So we can use FPGAs to achieve very efficient designs. And we also want to enable direct hardware descriptions, so we can use hardware description language to do so. And if we want to do it easier, do not want to write the hardware description languages, we just write high-level synthesis code. We want to bridge software and hardware domains and making acceleration more accessible. Yeah, that will be a very good starting point. We can use a high-level synthesis. There are already many tools that will compile software algorithm implementation into the hardware. The fifth point that there are design automation tools that will further simplify the hardware design, and there are more for you to consider. If you can really utilize machine learning, artificial intelligence, like language models well to do this kind of task, it will be great for the hardware community to have such kind of efficient tools. And nowadays, their exploration of LLMs are very simple, so there are a lot of rooms to do here. I think that's all. Here are my two small papers, so just the toys as undergraduate projects. And I will also try to make the PDF online after the presentation. So that's all.